Okay guys, in this video we're going to be going over the dot product, part 3. This over here we're going to come up with a massive theorem that's going to really change what we think of as the dot product. I'm going to tell you the theorem first, and then I'm going to give you the proof. Let me change markers for a quick sec. The theorem says that if I do the dot product between two vectors, I'm going to end up doing the magnitude of one vector times the magnitude of the second vector times cosine theta, where theta is the angle between them. So if I have this vector over here, that vector over there, the dot product between those two is going to be the length of that times the length of that times cosine of the angle in between them. And now for this proof. So we do this proof by using the law of cosines. But before we get started, we're going to need to figure out what this right over here is. So again, there are two ways to do it. One, we could say, here, I'll work over here. One, we could say the vector A plus that is equal to that vector over there. So I'll just call the box for now. And then we see that that box is equal to B vector minus A vector. So we can put in B minus A. Another thing that we could do is we could rearrange all of this stuff around to move that back, that down, whatever you want to do, so that you could end up with that being a very simple vector to solve for. Okay, all right, I can keep that up. So now the proof, it uses the law of cosines. And if you want to look up what the law of cosines, I might make a video of that, or you could check a textbook or the internet for what the law of cosine says. So we need to figure out what this is. We're going to say that the magnitude of the B vector minus the A vector is equal to the B vector, the magnitude of the B vector squared plus the magnitude of the A vector squared minus 2A B cosine theta. And so now I'm just going to expand this out. And so I'm going to, like we said in the last one, if I have a C vector squared, that's the same thing as C dot C. So I'm going to use that property to expand this out. It's going to end up being B minus A dot B minus A equals, and then I'm going to expand that out into B vector times B vector plus A vector dot A vector minus 2A B cosine theta. And now I can go ahead and expand this out. I'm going to say B dot B dot, and then minus A B. Again, there's dots in all of these. Minus A dot B, and then plus A dot A, and that equals B dot B plus B A dot A minus 2A B cosine theta. And we can cancel this out with this and this out with this. So we're left with minus 2A dot B equals minus 2A vector. Oh, I didn't put my vector sign over there. A vector B vector cosine theta. I could cross out those. And I'm left with A dot B equals the magnitude of the vector A times the magnitude of the vector B times cosine of theta. This right here is a very important theorem that we have just proved. And so there's some things to look back on, to remark on, if you will. So if we have A dot B equals 0, and we also know that the magnitude of A and the magnitude of B are not equal to 0, then we know that it's perpendicular to each other. A is perpendicular to B. That's because then the cosine of pi over 2 equals 0. So if I ask what's the dot product between these two vectors, the answer would be 0 because the cosine is going to be pi over 2 and cosine of pi over 2 equals 0. So their dot product is also equal to 0. Now you should also notice that you could have the dot product be a negative number if the cosine is between pi over 2 and 3 pi over 2 in the second and third axes. And that's not a mistake. That really helps you out sometimes. So anyways, thank you much for watching, and goodbye.